As you might remember from last time, there are 5 user interface boards. There is the data board, the address board, the memory access board, the CPU control board, and finally the status board. The CPU control board generates the clock, which is provided to the CPU and to the status board for visualization. When the CPU control board HAL run switch is in run mode, the CPU is considered to be in control and drives the address bus, and the read-write signal dictates the direction of the data bus, whether the CPU or the memories drive the bus. In this mode, the address and data boards are passive and only visualize the contents of the buses. If the HAL run switch on the CPU control board is switched over to HALT mode, the DMA, which is the direct memory access, signal goes high to indicate that someone else, that is not the CPU, drives the address bus and the read-write signal. The DMA signal is inverted and provided to the address board and memory access board as an active low output enable signal. The address board is now driving the address bus and the memory access board drives the read-write signal. And when the DMA signal is high, the bus enable signal on the CPU is low, which causes the CPU to back off from driving its bus signals. Let's look at what happens when the user initiates a write operation. When the write switch on the memory access board is activated, the read-write signal goes low and the output enable signal to the data board is driven low, causing the data board to start driving the data bus and thus issue a write operation to memory. When the system is in halt mode, one can use the single-step switches in the CPU control board to advance the state of the processor. But when doing so, the DMA must be temporarily deactivated to give the CPU control over the bus to read and write memory. The data board is the simplest of all the UE boards. There are 8 inverters connected to the data bus, and when a bit of the bus is high, the connected inverter output is low, and that lights up the corresponding LED. The inverter is a 74LS04 capable of sinking 20 mA per output, which is more than enough to light up the LED. This happens irrespective of who is driving the bus. If the output enable is activated, the switches to this board drive the bus. Before we take a look at the address board, we need to understand the signals LSW and INC coming from the memory access board. There are 2 switches, read and write, which can have 3 positions each. The central position is neutral. The position at the top performs a read or a write operation from the address that is specified by the address board switches. The position at the bottom increments the address by 1 and then performs a read or write operation. The first step is to debounce the signal to create a nice pulse at least 50 milliseconds long. If any of the switches are in the upper position, the pre-LSW signal is generated, which is shaped into a short, nice LSW pulse that is sent off to the address board. This tells the address board to load the values of the switches into the address register. If any of the switches are in the lower position, a pre-INC signal is generated, which is also shaped into a nice INC signal and sent off to the address board, telling it to increment the address register by 1. There are 2 LEDs indicating a read or a write operation. These are sitting outside the buffer, so they always indicate the status independent of who is actually driving the signal. When any of the 2 write signals is triggered and the output enable is activated, this card drives the read-write signal low. Similarly, the read-write signal is driven high when the switches are in the idle position or when a read is performed and the output enable is activated. The 10 microsecond delay is there to make sure that the write signal is delayed a little while the address register is being incremented. This is to prevent that more than one address is written to during the address stabilization phase. Now that we know what the INC and LSW signals mean, we can have a look at the address board. There are 3 major parts: the set of switches, a cascade of 4-bit adders, and 2 8-bit registers. Much like on the data board, there is a set of LEDs outside the register, which indicate the status of the bus irrespective of who is actually driving the bus. When the LSW pulse comes, the PL inputs on all counters go low, which causes the address to load the values set on the switches. When the LSW signal goes low again, the logic makes sure that there is a positive flank on the clock input of the two 8-bit adders. This causes them to store the value of the adders, which previously was the value of the switches. If the output enabled signal is activated, this will then be the value driven on the bus. When the ink pulse arrives, it goes into the adder cascade, and thus the value stored in the adders will be incremented by 1. When the ink signal goes low again, the logic makes sure that the registers store the adder values in the same fashion as in the LSW case. Now that we have a basic understanding of the data board, the address board, and the memory access board, let's have a look at the status board before we tackle the CPU control board. The design for driving the LEDs on the status board is very similar to the other boards. The interrupt and NMI signals are active low, but I want the LEDs to light up when they are active rather than when they are high. I think it makes a better user interface to only light up things that warrant some kind of attention. That's why there are double inverters on the NMI and the interrupt. Similarly, I want the clock LED to light up when you press the single step button, which means another inverter. But since I already had used up 6 of them in the 74LS04 and I wanted to save some space, the last inverter was implemented by using a transistor. For the switches on this board, I chose a NAND-based debound solution instead of the RC filter previously shown, mostly because they're fun and it fits nicely into a single 74LS00. I used 2 transistors to pull down the interrupt and NMI signals. Note that it is on this board that these 2 signals actually are pulled high. In iteration 2, there will be other sources that can pull these signals low, such as expansion boards, in order to get the attention from the CPU. Now, let's turn our attention to the CPU control board. The CPU control board is the most complex of all the boards, mostly because of the many switches and buttons. It is divided into 2 different sheets, and this is the first one. The clock and instruction step buttons are debounced and the signal is sent off to the next sheet. The run halt switch and the reset button is treated in the same way. For the clock generation, however, we have 2 controls. The potentiometer P1, which provides the R part of this RC oscillator, and the multiplier switch that attaches different sized capacitors to it. This works, but practically the 1 MHz frequency range proves to be too big for this approach. In order to cover the 1 to 1 MHz range, every switch position must cover 2 orders of magnitude, that is, 1 Hz to 100 Hz and 100 Hz to 10 kHz and so on. That is hard to do with a single turn potentiometer. This design will change in iteration 2, where there will be a rotary switch with 6 positions instead, giving the potentiometer a span of a single order of magnitude. The generated clock, called the raw clock, is sent off to the next sheet. The second sheet is both more and less complicated than it looks. Here I am a little bit inconsistent with the naming. What is known as the DMA on the main board is here referenced to as UMA, User Memory Access. I really can't make up my mind on which name is better, but they are referring to the same thing anyhow. Remember that I said that a DMA signal has to be disabled whenever the clock ticks in halt mode? This is the logic that takes care of that. UMA is only high when in halt mode and when neither the clock nor the instruction buttons are pressed. The stuff in parentheses can be ignored. They are leftovers from some experimentation. If we are in run mode, the run signal is high and the raw clock signal is emitted as the proper clock in the system. When we alter the HAL state, this emission stops. The emitted clock is driven to 1 when we are in halt mode. It is during the halt mode that one can use the stepping buttons. When pressing the clock step button, the signal goes through an inverter and creates a negative pulse on the emitted clock, and that is all there is to clock stepping. Instruction stepping is slightly, but not much, more advanced. After reset, the D flip-flop is initialized such that Q is 0, and thus the inverted Q is 1. When the instruction step button is pressed, the D flip-flop clocks in a 1 to Q, which causes the inverted Q to go to 0. This in turn makes the raw clock pass through the OR gate and to be emitted as the out clock. This continues until the sync pulse goes high. This happens usually when the CPU fetches the next instruction, and we will exploit this fact to stop the raw clock from being emitted. The sync pulse is shaped into a short nice pulse, which is inverted. This inverted signal goes to the D flip-flop and resets it, which causes Q to become 0 and the inverted Q to become 1, and that in turn stops the raw clock from passing through the OR gate, and the clocking to the processor stops. There is another occasion besides the instruction fetch when the sync signal goes high, and we will exploit that later, but I will come back to you on that. We have made a quite detailed tour of the iteration 1 construction. Now it is time for this construction to leave the space of ideas and dreams and to enter the physical universe. Unfortunately, this is the end of this episode. In episode 2b, we will build and run iteration 1 of the Alt6502. See you next time!